Hello, screen visible?
Yes,
Yeah,
Professor
okay,
Gupta,
Rahul.
screen is visible and your voice is also very much clear.
Thank you. So, you might have in this series of lectures, you might have understand various concept of on optimization, right? So, you might have seen that what optimization model basically means. So, optimization model basically means that you have to optimize objective function subject to some set of constraints. Right. I mean, I want to say that suppose you have maximization or minimization of some function fx subject to some set of constraints, say gx less than equal to 0, j from 1 to m, for example, right? So such model are basically called an optimization model, right? Where you have to optimize a function subject to some set of constraints or conditions. Now, this function which we have to optimize is called as objective function. We already know this, and these are called constraints. These set of conditions or restrictions on the variables are called constraints. Such optimization problems are broadly classified into two categories. One is linear programming problem, and other is non-linear programming problems, right? So what is linear programming problem? Let us first of all see what is linear programming problem, and then non-linear programming problem we will discuss in next lecture. So this problem is this session is devoted to linear programming problem only. So what linear programming problem means? Linear programming problem means the objective function f as well as all constraints gj's for all j, all are linear, right? If all are linear, we say it's a linear programming problem. And if it is not linear means non-linear, right? So not linear means either objective function or at least one of the constraint is non-linear. Then we say that it is a non-linear programming problem. Now, so how can we formulate a non-linear linear programming problem in general, right? So here, suppose you have this problem. I'm simply writing one example for you. Suppose you are having 2x1 plus 3x2 plus 4x3, a three variable problem in which you want to maximize this function subject to some conditions. Say x1 plus x2 minus x3 less than equal to 4. Suppose minus x1 plus 2x2 plus 4x3 less than equal to 6, and all variables are non-negative, right? So this problem is clearly a linear programming problem, because here the objective function which is given to us all are linear. Objective function is linear as well as all constants are linear. So this problem is clearly a linear programming problem. Now this problem can also be recast in this way. You can write maximizing f equal to 2, 3, 4, and then you can write x1, x2, x3 over here, right? Subject to what are the conditions you are having: 1, 1 minus 1, minus 1, 2, 4, and right, and this is your x1, x2, x3, right? And this is less than equals to what is right hand side, 4 and 6, right? And x1, x2, x3 all are non-negative, all are greater than equal to 0, right? So now this can be further rewritten as in this form: maximizing f equal to. Now if I suppose that this is our c, right? C transpose, and this is our x, right? This is x, this is c transpose, and this I suppose is a matrix A, and this I suppose x as above, and this is right hand side B, right? So this problem can be written as C transpose X subject to AX less than equal to B and X greater than equal to 0. So why I am writing in this way? What is the purpose of writing in this form? I want a general representation or general framework or general model to write a linear programming problem, because there are many theories, properties of a linear programming problem, and I to prove or to disprove such properties, I need a general framework of a model. So now, if it is a 10 variable problem, also I can write any linear programming problem in this format, right? Here C and X are basically are the vectors in Rn, column vectors in Rn, right? A is a matrix of order m cross n, is a matrix of order m cross n, right? B is a vector in Rm, and this 0 is basically not a single 0, it is a vector in Rn. So in this way, I can always represent a linear programming problem. So this is the first thing, right? Okay. So now we can talk some of the properties of linear programming problem first of all. So to understand some of the property of linear programming problem, first of all we have to understand what is convex set, right? You most of you might be knowing what convex set is, but for those who are not knowing what convex set, just I want to explain them what is convex set, right? Convex set. So then after discussing convex set, I come back again to linear programming problem. This problem P. I will again come back to this, and will explain you what do you mean by convex. How convex set is important to study linear programming problem, right? So what a convex set basically means, you can easily see a figure. For example, you take a circle, you take all the point inside the circle, right? So this set is a convex set because if you take any 2 point inside this region, you draw the line segment. The line segment joining these 2 points lies totally inside this set. You take 1 point here, 1 point here, join the chord lies completely inside the region. And if it is true for any x1, x2 in this region, then we say the set is a convex set. So this is a convex set, right? However, if you take such type of region, suppose you take such type of region over here. Now, if you take a point here, 1 point here, 1 point here, and join the chord some lies outside the region. It is not lies entirely inside the region. So this set is not a convex set. That means if you have to see whether a set is convex or not, you take any two arbitrary point in the region and you try to visualize that the line joining the 2 points lies totally inside the region or not. If it is lying totally inside the region and it is true for all the points, all x1, x2 in the region, then we say the set is a convex set. However, if there exists a pair for which this property is not holding, we will say that the set is not a convex set, right? Mathematically, how we define it? Mathematically, we can define in this way, that we take 2 points, say S is a subset of Rn, right? Is a convex set if and only if for all x1, x2 in S and lambda between 0 and 1, the CLC of these 2 points, lambda x1 plus 1 minus lambda x2, must be in S. What this represent basically? See, you have a line segment x1 and x2 here, right? You take lambda equal to half, so this will give midpoint of x1 x2, something here. You take lambda equal to 1 by 3. Yeah, lambda should be in between 0 and 1. You take lambda equal to 1 by 3, so you will get some other point, but all the points will lies in between x1 and x2, right? So this is your x. So you vary lambda, you vary x1 and x2, and for any x1 x2 and for any lambda between 0 and 1, the this is called convex linear combination. Convex linear combination. So convex linear combination of those 2 points must be in S. If it is holding, then we say the set is a convex set. Is it clear? Is it clear? I hope you are listening me, right? Okay. Okay. So now let us go ahead. We have taken this as a linear programming, general model of linear programming problem. This as a general framework of linear programming problem, right? Now, first of all, the first property of LPP is that you take any LPP. Any LPP can be written in this frame, in this type. We can always write. So if the first property is basically the feasible region. The first result is basically the feasible region. The feasible region. Okay. The feasible region. The feasible region of any LPP is always a convex set. So you take any LPP, and if you draw the feasible region is always a convex set. So how can we show this? So I am just giving you the hints of the proof that you take any 2 points in the feasible region. Suppose S is a feasible region where S is simply all x in Rn such that Ax less than or equal to B and x is greater or equal to 0. This is a feasible region, right? Now you take Z as a CLC of these 2 points, the convex linear combination of these 2 points for any lambda between 0 and 1, right? We need to show, if we want to show that S is a convex set, we need to show that this Z is in S, right? So how we can show that Z is in S? We have to show that AZ less than or equal to B and Z is greater than or equal to 0. So what is AZ? AZ is basically A into lambda x1 plus 1 minus lambda x2, right? Which is lambda times ax1 plus 1 minus lambda times ax2, which is and ax1 is less than or equals to B and ax2 is less than or equal to B because x1 x2 is in S. So this is less than or equals to lambda into B plus 1 minus lambda into B, and which is equals to B. And of course, that is greater than or equal to 0 because lambda is between 0 and 1, and x1, x2 both are non-negative. So we can, from this, we can say that Z belongs to S. And this implies S is a convex set. Right? So in this way, we can see that feasible region of any linear programming problem is always a convex set. So for example, you take a linear programming problem, right? Now let us take one linear programming problem and try to visualize it. Are you understanding? Please ask your. You can write in your chat box if you have any doubt or anything you want to ask. Any doubt till now? Hello. Any doubt till now?
Participants, if you have any doubt, any question, you can write in the chat box. Professor Gupta, many participants, I think they don't have any doubt. They are writing no, sir, clear, sir.
No, they have not written anything. No?
No, Professor Gupta, they are writing. I mean, you just seen the chat window. You can
Yeah,
maximum.
chat. The last chat is 10:58 a.m.
I think it's not updated in your system, Professor Gupta, because many participants are writing no sir, clear sir, no
Oh,
sir,
really?
no doubt sir, no doubt sir. At least 9
Oh,
participants.
you are, but I am not able to
You,
see.
you 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 can scroll down on or you can this just go to the WebEx platform again and you can see the chat box.
Yeah, chat box is in front of me. Okay, let me see once again. Hmm.
Yeah, you see there, right?
Okay. I don't know what is going on because I am not able to see here.
But at 11:20 they are writing no, sir.
Oh, really? Anyway, so
Yeah.
let me
No, no,
start.
but in your also it is coming, I think. Na, in your window also,
No,
I
it
can
is
see in
not.
your window.
It is not coming actually. I don't know what is the reason. The last updated message is at 10:58 a.m.
Uh,
So there is something I don't know what is there.
you can go, yeah, in everyone, yeah, in everyone you must see. Yeah.
Just wait for 2 minutes. I'm just looking into it. What is the problem
Yeah,
actually?
yeah, please take your time. Please take your
Yeah,
time.
yeah,
Yeah.
please 2 minutes. Okay, okay. Hello.
Yes.
Yes, 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 yes. Now it's okay.
Mhm.
Yeah. So, so, feasible region of a LPP is always a convex set, right? Now let us take one example, right? Now let us take one example. So you can take one example over here, maximizing z equal to 5x1 plus 3x2. Subject. Let us take a very simple example to understand the graphical representation of a linear programming problem, right? So I have taken a very simple example now. So you all know that this is a linear programming problem because the objective function as well as all constraints are linear, right? Now, if you want to solve this problem, how can we solve? How can we solve this problem? You can see it is x1 and it is x2, right? The first constraint is x1 plus x2 less than equal to 4. You can put x2 equal to 0. You will find x1 equal to 4 here, right? And x2 equal to 2, right? So this second point. So this is the first constraint, right? So less than equal to 4 means towards origin. You take 0 0, for example, you put 0 0 over here. 0 plus 0 less than equal to 4, that means true, that means shade toward origin, right? So now you take this line. So this is x1 equal to 3 and x2 equal to 3 here. And you plot this line. So this is the second line, right? So this is L1 and this is L2. And again, you take 0 0 as one point and you put 0 plus 0 less than equal to 3. That means true. So that means shade toward origin, right? And x1, x2 should be non-negative also, and non-negative only in the first quadrant. So this means this is your feasible region, right? So you can easily see that this feasible region is a convex set. However, we have proved it here that for any LPP, the feasible region is always a convex set, which is true here also, right? Of course, it will be true. Now, these points, these points, which are the corner points or the vertex of the feasible region, There are four vertex or the four corner points of this region. Now there is a fundamental theorem of a linear programming problem which states that if the region is bounded, see here the region is bounded, right? Feasible region is bounded. If the feasible region is bounded, then the maxima or minima of a linear programming problem is always exist only at the corner point or the extreme point. So that means O, A, B, C. These are the four corner points, right? So the maximum minima of this problem will exist at O, A, B, or C. So what is the value of z at O? O means origin, right? Origin, right? So the value of z at O will be 0. Now value of z at A, right? What is A point? A point is basically A point is 3 comma 0, right? 3 comma 0. This point is basically, this point is 0 comma, it is okay. What is C point? C point is C point 3 and 3. So there is some problem, I think. Let me draw it again. Give me 2 minutes. So what are the various points? Let me see. See, this is your x1, this is your x2, this is 4 comma 0, right? This is your 2 comma 0, right? This is 2 comma 0. So this is your first line, and this is your 3 comma 0, 3 comma 0, and this is 0 comma 3. So this is your second line. So this is O A B C, right? So this A point is basically 3 comma 0. This point is 0 comma 0. This point is 0 comma 2. And this is a point of intersection of these two lines, which is basically x1 equal to 1 and x2 equal to 1 basically. And when you put x2 equal to 1, x1 equal to 2. So this point is 2 comma 1, right? Then this is a feasible region. So what is z at 3 comma 0? A point, this is 15, right? What is z at 0 comma 2? This is your 6. And what is z at 2 comma 1? Is simply 10 plus 3, that is 13, right? So this 15 is giving you the maximum value of this objective function. And at which point? At the point, yes, yes, Ankita, what is your point? Yeah, A point, right? So this A point is a point of maxima. No, no. You think that starting it will be a very basic lecture, and then I will go to the simplex method, and how simplex method works. We will explain clearly, right? So what basically extreme point means? Extreme point basically means if you take this as extreme point, this point as extreme point, so this point cannot be expressed as CLC of two distinct points of the feasible region, right? You take one point here, one point, you cannot find other 2 points in the feasible region such that this point can be expressed as CLC of two distinct points of the feasible region. This is mathematically we can define this point, right? Now come to basic feasible solution. BFS. So this also you might understand what BFS means. Suppose you have AX equal to B as a system of linear equations. A is a matrix of order M cross N, right? Where M is less than N, and rank of A is M, right? Then you put N minus M variables equal to 0. Put N minus M variables equal to 0. then we get our new system, which is bx equal to b, right? Because bxb equal to b, right? Because now you left with only m equations with m unknowns, m equations with m unknowns. So the variable which we are setting to 0 are called non-basic variables, and the variable xb basically here, which we obtained by solving this equation, is called basic variable. So this is your basic variable, right? Now the solution of this equation, the solution of this equation is basically called uh, is basically used to find out basic solution of this equation, basic solutions. The xb, whatever we have obtained from this, is called basic solution, right? Now if all basic variables, if all the basic variables are greater than or equal to 0, then it is called basic feasible solution, right? Right, we may have, see, here these points 0 0, 3 0, 2 1, and the 0 2. These are your basic feasible solutions. These points, say this point is E and this point is D. This D and E are the basic solutions but not basic feasible solutions. So in this case, you will be having 6 basic solutions but only 4 basic feasible solutions. Because for basic feasible solutions, all variables must be non-negative, right? Okay. So now let us see. Is it clear up to here? Basic feasible solution is okay. 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 So now, so in this case, usually there is a one-to-one correspondence between the extreme point and basic feasible solution. One extreme point will correspond to one basic feasible solution, or one basic feasible solution will correspond to one extreme point. When it will happen? It will happen when all basic variables are strictly greater than 0. But if there is a basic variable in basic feasible solution which is equal to 0, then this is a case of degenerate BFS. And in the case of degenerate BFS, there may be more than one BFS which may correspond to the same vertex. Are you getting my point? I want to say that there are two possibilities. One possibility is that there is one-to-one correspondence between the BFS and the extreme points, right? When it will happen? It will happen when all basic variables are strictly greater than 0. But if there is a basic variable in BFS which is equal to 0, there may be a case when more than one BFS will correspond to the same vertex, right? Right. Now, graphical method of solving a linear programming problem will applicable only for two variable problems. Say in this problem, the problem which we have seen here, this is a two variable problem, so we can solve it using graphical method. But how we can solve a problem of 3 variable or 4 variables if we are having? So we can solve such problems using simplex method. Now, first of all, let us try to understand that how simplex method works. You all might have, some of you might have been knowing that what simplex method is, in which we enter a variable, leave a variable by some rule, and then we move from one table to another table to find, so that in each table the value of the objective function is improved, right? But how the simplest method works? What is the fundamental concept behind the simplex iterations? So let us try to understand this by an example. So please write in the chat box if you have any doubt, right? So let us take one simple example. Let us take one simple example to understand that how simplest method works, right? So let us take this example. However, we can solve the same problem using graphical method as well, but this is just an illustration that we can solve that how to solve such problem using simplex method, right? So first of all, this is a linear programming problem, right? We already know that. And we can convert this less than equal to type inequality by an equation using slack variable here, right? Because the left hand side is less than equal to right hand side, that means we have to add some non-negative quantity in the left hand side here so that it become an equation. So that is minus x1 plus 3x2 plus s1 equal to 10, right? Similarly here also, because left hand side is less than equal to right hand side, that means we have to add some non-negative quantity in the left hand side to make it an equation. So x1 plus x2 plus s2 equal to 6, and all variables non-negative. Now to start simplex iteration, first of all we need an initial BFS. Now what do you mean by initial BFS, right? So initial BFS is basically uh, I am just taking one BFS. Yeah, for simplicity, I am taking x1 equal to 0 and x2 equal to 0. Is slide is running now? Rupesh, is it okay? Okay. Okay. So take x1 equal to 0 and x2 equal to 0. See, how many variables we are having in total here? 4 variables, right? And how many equations we are having? 2. So for basic solutions, we have to put n minus when m variables equal to 0. That means we have to put 4 minus 2 equal to 2 variables equal to 0. So you can put any two variables equal to 0. There are many possibilities. So I am putting x1 equal to 0 and x2 equal to 0. So I will get s1 equal to 10 and s2 equal to 6. And since these are greater than equal to 0, so we will say that this is a basic feasible solution. Clear? It is one of the basic feasible solution. So in this case, z equal to, what is the value of z at this BFS? This is, you put z equal to x1 0, x2 0, so z will be 0 here. Now we find improved BFS if exist. Now how we will find improved BFS now? We don't know. Is the point which we got here, is it an optimal solution? We don't know, may or may not be, right? So how we will check whether the given BFS is optimal or not? So we will try to see improved case. How we will see? We will find relative profits corresponding to each variable, corresponding to each non-basic variable. What are non-basic variables? The variables which we put 0, right? Here here these two are the non-basic variables, and these two s1 s2 are the basic variables, right? What are relative profit? Let us see. We take this x1 variable and we increase it by unit value, right? We increase x1 from 0 to 1, for example, and we try to see what will be the impact of increase in the unit variable of x1 in the value of z. right? So we put x2 equal to 0. X2 is remains 0. So when x1 is 1 here in this equation, when x1 is 1 and x2 is 0, x1 is 1 and x2 is 0. So s1 will be 11, right? S1 will be 11. And what will be S2 from second equation? When x1 is 1, x2 is 0, x2 is 5. Now, is it a BFS? No, it is not a BFS, because for BFS, two variable must be 0, but it is only one variable which is 0. But it is a feasible solution. It is not a basic feasible solution, but it is a solution, right? So at this point, what is Z? If you put Z, so when you put x1 equal to 1 and x2 equal to 0 in this objective function, you will get Z is equal to 1. So is the value of Z improved? Yes. It is initially it was 0, now it is 1. That means the initial BFS is not optimal. We have to go for some other BFS to find out the optimal solution, right? Now similarly you can find out, so this is basically relative profit corresponding to x1. What is relative profit? Relative profit is the increase in the value of the objective function per unit increase in the value of the variable. You have increased the value of the variable x1 from 0 to 1, and you are seeing that how much the value of z is improved. That is basically the relative profit corresponding to x1, or the corresponding to non-basic variable. The same I will do for x2 also. x2 I will increase from 0 to 1, keep x1 equal to 0. When I put it here, what s1 I will get from this equation, the first equation, I will get s1 as 7, right? And s2 as 5 again. It is a feasible solution, no doubt, but it is not a basic feasible solution. So from here I will get z as 5. So the relative profit corresponding to x2 is more than relative profit corresponding to x1 in this case. What does it mean? It now it is, see, one thing is clear that the initial BFS what we have checked is not optimal. Is not the point which is giving the maximum value of z, right? If it is not optimal, that means we have to find the improved BFS. Now for improved BFS, we mean that the out of these two non-basic variables x1 and x2, one variable must become basic variable, and out of these two basic variables, one variable must become non-basic variable. Then only we find a new BFS, which is an improved BFS. Now the question is how we will decide that which variable will leave or which variable will enter. I mean, which variable will become basic from the non-basic variables, and which variable will become non-basic from basic variables. How we will decide that? See, here the relative profit of x2 is more than relative profit of x1. That means if we enter this variable, that means if we enter this variable, right? Wait. That means if we enter this variable, if we enter x1 x2, then the value of z will increase by the maximum amount. So that means enter x2. Enter x2 means x2 will become basic variable from the non-basic. Now out of, and x1 will remain non-basic variable. Now out of s1 and s2, one variable must leave the basis. Which variable will leave the basis? Now we will decide from these two equations. You can see here x1 is 0 because x1 remains non-basic, right? So what is s1 from the first equation? S1 will be what? S1 will be 10 10 minus 3x2, right? And from second equation, s2 will be what? 6 minus x2. Now you take different values of these x1 and x2, right? x2. You put x2 equal to 0, right? Let me write it here. S1 is what? 10 minus 3x2. S2 is what? 6 minus x2. You put x2 equal to 0. When you put x2 equal to 0, this is 10, this is 6. When you put x2 equal to 1, this is your 7, this is your 5. And when you put x2 equal to say 10 by 3, this is 0 and this is 18 and this is 8 by 3, right? And after this, when you put some x2 value, this become negative. This become negative. What does it mean? That this variable is leaving first. This is leaving first. That means this leave the basis, and this will retain in the basic variables. And so, how we will decide that which variable will leave the basis? See, this is your 10 by 3, right? 10 upon 3. See here, 10 by 3, and this is your 6 by 1. The minimum ratio is the minimum value. Minimum, if you see the minimum ratio, 10 by 3 is here. So this variable should leave the basis, right? So this rule is called basically minimum ratio rule, right? So now, so again, we will. So what is the improved BFS now? What is the improved BFS now? For improved BFS, X2 and S2 are the basic variables, and the other two, X1 and S1, are the non-basic variables. Right? You can find out the value of Z also using this information, and you can observe that the value of Z is, of course, very high than Z equal to 0, which is the initial BFS, right? Again we will see that whether this BFS is optimal or not. We will again go for relative profit corresponding to X1 and S1, right? If relative profit are positive, that means the BFS which we have find is not an optimal one, and we will enter the variable which is having the maximum value of relative profit, and again we will leave the variable by minimum ratio rule. The process will keep on going till all relative profits are either 0 or negative. If relative profits are 0 or negative, that means further improvement in the value of Z is not possible. And the process will keep on going till relative profits are greater than 0. Right? So is it clear? Okay. So let us take one table, and we will try to see that how the table works now. So now it will be clear to you from the table also. So let us take the same example. This is example is basically what? Example is maximum Z equal to x1 plus 5x2, subject to what are the conditions? The conditions are minus x1 plus 3x2 plus s1 equal to 10, and x1 plus x2 plus s2 equal to 6, and all variables non-negative. Right? So let us take the first table now. So in the initial table, we take basic variables as, wait, we take basic variables as s1 and s2, right? So basic variables s1 and s2. right? And this is your CB, cost of basic variables. This is your right hand side, or right hand side you can put here. It is in our hand whether we can keep it here or here. Okay, so this is your right hand side B. So this is your 10, right hand side first 6, right? X1, X2, S1, S2. These are the 4 variables. What the column of S1? Column of X1 is what? Column of X1 is -1, -1, -1 plus 1, right? -1, 1. This is 3, 1. This is 1, 0. This is 0, 1. And now we will find Zj minus Ej's over here. Zj minus Ej, which are simply these Zj minus Ej is simply negative of relative profits. How we compute that? We will see here. Cj's or what are the cost of the objective function? Cost. This coefficient is 1. This coefficient is 5. This is 0. This is 0. Right? The cost of C1 S1 is 0. This is 0. From here, this is 0. This is 0. Right? Now to find Zj minus Cj, we simply make one small calculation. Cb into Xb minus Cj. Right? For Zj minus Cj's, Zj minus Cj's are simply Cb into Aj, you can say, minus Cj. This I am calling as A1 table, A1. This I am calling as A2, for example. This I am calling as A3. This I am calling as A4. So when you multiply these two, 0 into -1 plus 0 into 1 is 0 into minus Cj, -1. So it is -1. This is -5. 0 into this plus 0 into this, -5. So this is 0, this is 0. So these values basically are the negative of relative profits. So Zj, Cj's are basically negative of relative profits. Okay. So which variable will enter, which is having most positive relative profit, that is most negative value of Zj minus Cj. So this variable will enter. And which variable will leave? You can find ratio 10 by 3. This is your right hand side, and this is your entering column, right? So 10 upon 3, and this is 6 upon 1. Which is minimum? Minimum is here 10. So this will leave the basis, and this one it will be your this will be your pivot element. The intersection of these two arrows will be your pivot element, right? So now you will make next table. How we will make next table, we will see here. So now this is basic variables are now S1 is leaving and X2 is entering. So this is your X2, this is your S2. So you might be knowing this how to make a table. I'm just trying to understand you that why this variable is entering and why this variable is leaving. How these iterations are going on. Number one. Number two, what are the various insights of these tables? I will try to explain you after completing this problem, right? So we will make one here. This pivot element will make one, and the this we will make 0. Why we are doing this? Why we are making pivot element as 1 and all other element as 0 in that column? I will explain you after this, right? So we make one here. We make elementary row operation. We divide the entire row by 3. So this is minus 1 by 3, this is 1, this is 1 by 3, this is 0, and this is 10 by 3. And you want to make 0 here with the help of this. So this minus one third of this minus one third of this will be 4 by 3, this is 0, this is minus 1 by 3, this is 1, this is 6 minus 6 minus 10 by 3, that is 8 by 3. And what are your ZJ minus CJs now for this table? That also you can compute by making 0 here with the help of this pivot element. So this you can make 0. Suppose this is R3 row. So you can apply one elementary row operation R3 to R3 plus 5 by 3 times R1. So 5 by, if you add 5 by 3 times this will make 0 here. So this minus 5 by 3 times this will be minus 8 by 3. This is 0. This is 5 by 3. This is 1. And this is your objective functions. Now, is this table optimal? Of course, no. Because still you are having one ZJ minus CJ which is negative. One ZJ minus CJ negative means what? Negative means that relative profit corresponding to X1 is positive. That means the BFS or the which is we are getting in this table, the second table, is not optimal, right? So we now enter this variable. We again leave by minimum ratio rule, right? Now this is negative, so this cannot be a pivot element. So the only case we will left with is a second element. Hello. Okay. So what is the pivot element? 4 by 3. So what is your next table now? And I hope that it is the optimal table. So is there any lagging? Okay. So now this is X2, right? And X1 is entered. So this is 4 by 3. You will make 1 here. You divide this, multiply the entire row by 3 by 4. So this is 1, this is 0, this is minus 1 by 4, this is 3 by 4, and this will be 3 by 4 means 2. Now in the first row, you can apply one operation that this plus one fourth of this to make it 0. So this plus one fourth of the 0, this plus one fourth of this is 1 by 3, and this 1 by 3 minus one fourth of this is 1 by 12. That means 4 minus 3, that is 1 by 4, right? And this plus one fourth of this is 1 by 4. This plus one fourth of this is what? 10 by 3 plus 2 by 3. That is 12, that is 4. So this will be 4, right? Right? And what this ZJ minus CJ now? This ZJ minus CJs all will be positive. You can easily see this plus 2 times this 0, this plus 2 times this 0, this plus 2 times this 1, this plus 2 times this 2. So now all ZJ minus CJs are positive, means all relative profits are either 0 or negative. This means this is an optimal table. And what is the optimal solution? Optimal solution is x1 equal to 2 and x2 equal to 4. This is the optimal solution, right? 2 and 4. You can check it from here also by putting this equal this over here. When you put 2 and 4, 2 and 4, 12 minus 2 is 10, 2 and 4 is 6. So it is also satisfying. That is quite obvious just to verify the values. Now there are some question arises from the table itself. What are those questions? In the initial table, why we already take S1, S2 as a basic variable? Why not some other initial BFS? Number one. Why we make pivot element as one only? Why always? Why not we keep it as it is and try to see some other solution? Why? Why we have not enter why we have not this minus 1 by 3 in the second table? Why can't it be a pivot element? So all these questions are arising from this simple question. So let us see one by one the answers of all the questions, right? So first of all you can easily observe that when you put x1 equal to 0 and x2 equal to 0 here. Yeah, okay, you see here, this is your table 1, this is your table 2, this is your table 3, right? In table 1, what are your basic variables? Yes, basic variables are s1 and s2, and non-basic variables are x1 and x2. The first table. What your basic matrix? What is basic matrix? Basic matrix is B. See, in basic variables, in defining BFS where I write B here. So this B is called basic matrix. So what is the basic matrix in this case? In this case, when you put x1 equal to 0 and x2 equal to 0, you left with s1 and s2, s1 equal to 10 and s2 equal to 6, right? So the basic matrix will be identity matrix. This will be 1 0 0 1. This is your basic matrix, right? So now this matrix is your basic matrix in the first table. Now when you put s1 equal to 0 and s2 equal to 0, you directly get s1 equal to 10 and s2 equal to 6. That is, you directly get the solution of, you directly got s1 equal to 10 and s2 equal to 6. That directly the values of s1 and s2, right? However, in the second table, this is your x2 and this is your s2. These are what? These are basic variables in the second table. In the table 2, basic variables are what? Basic variables are h2 and s2, and non-basic variables are what? The remaining one, x1 and s1, right? See, in this, what is the constraint? Minus x1 plus 3h2 plus s1 plus 0h2 equal to 10, which is your first equation. Similarly here, 1x1, 1x2, 0s1, 1s2 equal to 6, the second constraint. You apply some elementary row operations in this equation, you will get second table. In the second table, the first constant will be minus 1 by 3 x1 plus 1 into h2 plus 1 by 3 into s1 plus 0 into s2 equal to 10 by 3. Second constant will be 4 by 3 x1 plus 0 h2, x2 minus 1 by 3 s1 plus s2 equal to 8 by 3. Second constraint. And these all constraints are equivalent in terms of solution, right? Now, now, if you are having identity corresponding to basic variables, then you will directly find out the solution of the basic variables. See, in these two equations, when you put x1 equal to 0 and x2 equal to 0, you are having identity matrix, and that identity matrix help you in determining the values of S1 and S2 directly. In the second iteration also we are making this as 0 1 and this as 1 0 and 0 1, which is the identity corresponding to the basic variables x2 and s2. This will help me in finding, because as soon as I put x1 equal to 0 and x1 equal to 0 in those new set of two equations, I will directly find out the value of x2 equal to 10 by 3 and x2 equal to 8 by 3. Are you getting my point? So that's why I am trying to make identity correspond to the basic variables, because simultaneously equations are changing. See, the same equation will not work for all the basic variables, because basic variables are changing, and we want to find out the solution or the values of these basic variables. To find out the value of these basic variables, we must have identity corresponding to these variables, so that we can find out the values of these basic variables directly from the table itself. Is it clear? So that's why we are making one as pivot element and try to make it identity corresponding to this variable, this with the help of this pivot element, right? Similarly, in the third table also, if you see in the third table also, we are having identity corresponding to the basic variables, so that we can directly find out what is the value of x2 and what is the value of x1. So this is the answer of the first question. So what is the basic matrix in this case? Basic matrix will be, what is the column of x2? 3 1. And what is the column of s2? 0 1. This is a basic matrix for the second table. For the third table, what are basic variables? The basic variables are x2 and x1, and non-basic variables are the remaining variables, that is s1 and s2. And corresponding to these two variables, what is basic matrix? Basic matrix will be x2. What is the column of x2? 3 1 and minus 1 1. 3 1 and minus 1 1. Right? Now let us try to analyze some other properties of this table. What are other properties of this table? Let us try to see. Okay. What this 10 6 represent here? Here, what this 10 6 represent? If you see the graph of this problem, which we have, if you see the graph of this problem, graph is here, right? At 10 comma 6, when s1 is 10, s2 is 6, what are values of x1 and x2? 0, right? Because those are non-basic variables. That means the first point of the simplex iteration will correspond to basically this point, origin, because x1 is 0 and x2 is 0, right? Now if you go to a second point, the second point of this table, which is this, right? So here x2 is 10 by 3. So what is graph is, okay, graph is not same. Okay, let me draw the graph of this problem once again to make you understand. So what is the graph of this problem? Okay, let me see. Okay, what I want to say, I just try to explain you by a graphical representation of this problem. This is your x1, this is your x2, right? What is your first constraint? Minus x1 plus 3x2 less than equal to 10. That means minus 10 is somewhat here and 10 by 3 is somewhat here, for example. So this is your first line, right? L1 towards origin, because less than equal to, right? The second constraint is x1 h2 plus less than equal to 6. That is, this is your x1 h2 less than equal to 6. Second constraint towards origin means this, and non-negative constraint means this is a feasible region. Now come to this point. So first point is 0 comma 0, which correspond to first point is 0 comma 0, which correspond to this point, right? The second is 10 by 0 comma 10 by 3, right? 0 comma 10 by 3 correspond to this point. That means we move from this point to this point in the simplest iteration. We first start from this O point and then we move to point A, right? And then finally we got x1 equal to 2 and x2 equal to 4. That means this point somewhere. That means we finally move to this point. So this is our optimal point. That means in simplest iteration, we always move from one BFS to another BFS, or from one vertex to another vertex, such that in each table the value of the Z is improved. We are improving the value of Z in each iterations, right? So this is the graphical picture of simplex table. Now you can see here, this is your B, right? And this is your B in the first table. In the first table. And in the first table, what is your B inverse? Is same, right? Of course, same. In the second table, what is a B inverse? That you can easily find, right? Because the 2 cross 2 matrix you can easily find, which comes out to be 1 by 3. You can easily check. 1 by 3 0 minus 1 by 3 1. Right? That means this table act as B inverse. Right? In the third table also, if you find B inverse, so this B inverse will be simply 1 by 4, 1 by 4, minus 1 by 4, and 3 by 4. You can verify. Is it correct? There is something in this. Let me check the calculation once again. Here, this calculation is okay. This one. You have made you multiply this entire row by 3 by 4, so 3 by 4 means minus 1 by 4. This is okay, and you are making 0 here. This plus 1/4 of this plus 1/4 of this is what? 1 by 3 minus 1 by 12, that is you take 12 LCM, 4 minus 1, that is 3 by 12, that is 1 by 4. That is correct. Is it inverse of this? Yes. Okay, we will verify once again. Afterwards we verify. Okay, now what I want to say that you can observe that this B inverse is here. Again, this B inverse is here. Why? Why we are having this B inverse at this position? This is your B. This is your B, right? Which I am getting from the problem itself. But B inverse are here. Why? What is the reason? The reason is, see, this is your identity matrix, right? See, you know that A into A inverse is identity, right? And when you make elementary operation and will make identity over here, so this will become A inverse, right? We know this by elementary operations, right? We know this. So this is your identity matrix. We apply some elementary operations and we make this as identity matrix over here. So the identity will act as A inverse or B inverse. Again, you go from first table to third table. This is your identity matrix, and you are making identity matrix correspond to S1 S2 now. So matrix coming below zero, below this table here, right? Below this table will act as B inverse, right? Number one. Number two, if you want to get, suppose you go for the second table, right? In the second table, suppose I want to find out what is the what how we can find out this value using B inverse, right? So this is very easy to find out using B inverse. See, what is B inverse of this table? Table 2, right? Table 2. B inverse is this, right? So we are focusing on table 2 now. B inverse is what? B inverse is simply 1 by 3, 0, minus 1 by 3, 1. And this is your A2. I want to find A2 using B inverse, right? What is your A2 of the original problem? Minus 1, 1, right? So B inverse AJ will be your new AJ. So B inverse A2. A2 is what? Minus 1, 1. B inverse is what? 1 by 3, 0, minus 1 by 3, 1. And this is minus 1, 1. You multiply these two, which is minus 1 by 3 and 4 by 3, which is your new A2, which is this column. Similarly, suppose I want to find out what is new B of this table using B inverse. So using B inverse, so B inverse B will be your new B of that table. Of that table whose B inverse we are taking. So B inverse is of which table? Second table, right? 0, 3, 1 by 3, 0, minus 1 by 3, 1. What is your B of the original problem? Go for the original problem always. 10, comma 6. It is 10, comma 6, right? So this when you multiply, this is 10 by 3 and this is your 8 by 3, which is right hand side of second table. So what I want to tell you that if I know B inverse of any table and I know our problem, this problem formulation. If I know problem formulation, I know the B inverse of that table. I can easily compute the other columns or any other entry of that table using B inverse. Is it clear? Right? Any doubt up to here? Okay. So suppose this is your B inverse, right? This is your B inverse of third table, right? And you want to compute what is right hand side. So you can take this as a B inverse, and then the original B is basically 10 comma 6. You multiply this with 10 comma 6, you will get back to 4 and 2. Correct? Okay. Now, how we will compute Zj minus Cj using B inverse? See, suppose I want to compute Zj minus Cj for any Aj. This is simply what Cb Aj minus Cj, right? What is your Aj of that table? B inverse Aj dash, you can say sometime. This is B inverse Aj minus Cj. So this is basically CB transpose we can put, because all we are taking as column vectors. So to multiply this, we need one as a row vector, another as a column vector. So CB B inverse Aj minus Cj. So this we can use to find out Zj minus Cj of any table. This Aj are from the original table. the original problem. These CJs are from the original problem, and this CB are the cost of basic variables, and this B inverse are is from that table for which we want to compute JJ minus CJ. So what we have concluded? We have concluded that if we have the information of B inverse, then we can, using this B inverse, we can easily find out the other entries of the table. We can even find out Jj minus Cj if we have the information of the problem and B inverse of that table. So using these information, we can find out simplex iterations, and we using relative profit and the concept of minimum ratio, we can see that which variable will leave or which variable will enter in the simplex method. Now, the one question which remain unanswered till now is why we have not entered minus 1 by 3 in this case. So see what is the second equation. Now let us try to understand why we have not taken that thing over here. What is second equation? Minus 1 by 3 x1, right? Second equation of a second table. Minus 1 by 3 x1 plus x2 plus 1 by 3 x1 equal to 10 by 3, right? The first equation. The second equation will be 4 by 3 x1 then minus 1 by 3 plus 1 plus 8 by 3. Okay. So is there any problem? Satinder is writing something. Is it happening with everyone or with Ankita and Satinder only? Oh, really? But here everything is fine. Anyway, sometimes okay. So now let us see here. Let us see that why we have, so here what are the basic variables x2 and s2, and one of the variables should leave the basis, right? So we have seen that the variable which is entering is x1. So x1 is entering, right? X1 is entering means x1 become basic variable, and out of these two, one should leave the basis. So out of s1 is 0. So s1 is 0. So that means x2 will be what? x2 will be 10 by 3 plus 1 by 3 x1, right? And what is your s2? S2 will be 8 by 3 minus 4 by 3. Are you getting my point? Because you can see from a table, if x1 is entering, this is clear because relative profit here is negative. Jj minus Cj is negative here, so this will enter, right? Okay. So this is entering, right? So this is entering means x1 should enter in the basis bracket and become basic variable. So out of these two now, out of x2 and h2, one variable must leave the basis, right? So that's what we are doing here in this table, right? Out of these two, one variable must leave the basis. So which variable will leave the basis? Now, if you take different values of this is your x1. If you put different values of x1, say x1 equal to 0, x1 equal to 1, x1 equal to 2, or other values, so this will never be 0. This will never be 0 or negative, right? This is keep on increasing, right? So this variable will never leave the basis. So what does it mean? It means that if this key element, pivot element, become negative, then this variable will never leave the basis. So that's why we never keep key element as a negative element. Pivot element we cannot take as a negative value. This is the reason. So since there is only one positive value here, so only this variable will leave the basis, because this variable will leave the basis sometime, right? After some iterations, after some point, this variable will leave, right? Is it clear? Is it clear? Okay. So suppose in the same table, if both are negative, what will happen? Suppose this is also negative. Let me take a suppose you have an example where you will get both element as 0, the entering column, and both all the pivot elements are, all the element in that column is negative or 0. Then what does it mean? Any idea? It means unbounded solution. Why unbounded? Because variables are both the variables cannot leave. They are keep on increasing. They are keep on increasing means value of z will keep on increase. Value of z will tends to infinity in this case. So this z will become infinite, and hence the solution become unbounded solution. We say such problems as unbounded solutions, right? Clear? So this is one illustration. I have shown you that if you take a linear programming problem, how can we solve using simplest iterations? What are the various geometrical as interpretations of various concepts involved inside simplest iterations that I told you. Now, simplex iteration is meant only for a specific type of linear programming problem, not for all type of linear programming problems. For which type of linear programming problem simplest method is meant for? It is meant only for that type of problem where uh, for linear programming problem where simplex is involved or applicable, is all constraint must be less than or equal to type. All constraints, and right hand side of all constraints must be greater than or equal to 0, and all variables must be greater than or equal to 0. So if you have these restrictions on the LPP, then for such problem, simplex method is applicable. Just taken one simple example: x1 plus x2 less than or equal to 4, minus x1 plus 2x2 greater than or equal to 6, and x1 x2 non-negative. Right. Now for this problem, simplest method is not applicable because this inequality is greater than equal to type and right hand side is positive. If it is, if it suppose it is -6 instead of 6, then we can multiply both the sides by -1 and right hand side become non-negative and all constants are less than equal to type. So simplest method will be applicable, but not in this case, right? So question is, how can we solve such problems then? So to solve such problems, we have two methods. I'm just briefing you one method, that is a two-phase method. So what happens in two-phase method? Let us try to see that thing. So this lecture, I think, also contains integer solution concepts also, I think, right? So after two phase, we will just have a brief idea of what integer solution means. We will discuss that also. So let us just give an idea of two-phase method. I'm just giving you the idea. So let us take one simple example of our two-phase method first of all, right? Okay, let us take this example itself, whatever I have written above. Take it plus here. Okay. Okay. So you can see that this constraint we can write as x1 plus x2 plus s1 equal to 4. The second constraint we can write minus x1 plus 2 x2 minus s1 s2 equal to 6, right? Because now the left hand side is more than left hand side, right hand side. So we have to subtract something from the left hand side to make it an equation. And all variables are greater than equal to 0, right? Now if we start simplest iteration, taking s1 and s2 as the basic variables, then the value of s1 becomes 4 and when the value of s2 becomes -6. But all variables must be non-negative. So this cannot be an initial BFS. So how can we start simplest iterations? We need an initial BFS to start. This is a very small problem of two variable. You can easily guess also one of the initial BFS, but in big problems where you are having 10 variables or 20 constraint or something like that, how can you find out initial BFS? So you must have a concrete algorithm to simplify all such type of cases, right? Only not only the small problem, even for a big problem, how can you see? So that's why people are trying to make an algorithm which is applicable for a general case, right? So of course, S1, S2, we cannot start as an initial BFS because it is not a BFS. So how can we start? We we reformulate this problem as this problem. See, we take one problem. We take one problem as maximizing z equal to 3x1 plus 4x2 subject to x1 plus x2 plus s1 equal to 4. In this constant, there is no problem because we are having identity correspond to s1 here. Minus x1 plus 2x2 minus s2, and we add an additional variable here called artificial variable. Now you might be thinking that adding a new variable change the system of equations. Of course, true. because this system of equations are not identical. So how we can guarantee that this solution will give you the optimal solution of the previous problem or the original problem? We cannot say. So how can we? What is the method to solve it? So what we do, we reconstruct a new objective function. Say it is z dash. What is a new objective function? We try to make this artificial variable to 0. As soon as this variable becomes 0, this problem will coincide with the original problem. And the advantage is that the last table, where a1 becomes 0, will give you the initial BFS of the original problem. And we can take that table as an initial table or the initial BFS to start the simplex iteration, and then we take this objective function and try to find out the optimal solution using simplex iteration, which we have already discussed. Now how can we construct a modified objective function? Now here you are having a1, right? We want to make this a1 equal to 0, right? So we can take this as maximum of minus a1. Why minus a1? Because you can easily see that this will be maximum only when a1 becomes 0, because all variables are non-negative. And as soon as a1 becomes 0, this problem will coincide with the original problem. And when it coincides with the original problem, that means that table, where a1 becomes 0, will give you the initial BFS of the original problem. Are you getting my point? Yes? Okay. So let us do. It has two phases. In the first phase, we eliminate, if artificial variable is not leaving the basis, then this means the problem is infeasible. Simple. Problem is infeasible. We cannot find out the optimal solution because problem itself is not feasible, right? If artificial variable leave the basis, that means we get back to the original problem, right? So the purpose of phase 1 is to eliminate a1 or artificial variable from the basis and to find out the initial BFS. And the purpose of a2 is to find out the optimal solution of the original problem, taking the initial BFS from the last table of the phase 1, right? So take now take phase 1, right? Phase 1. So in phase 1, this problem we will try to solve in phase 1, right? So what is the problem? We apply a simplex table only. The method is same, but only the thing is that we need to be think little bit more. All right. Now this is your x1, x2, s1, s2, and a1, and this is your zj minus cj's again, as we already seen. Basic variables here are s1 and a1 because they are making identity in the first table. Right hand side are 4, 6. 1 minus 1, 1, 2, 1, 0, 0 minus 1, 0, 1. Cj's are what? Cj's are 0, 0, 0, 0, minus 1. It is 0, it is minus 1. So it is 1, it is minus 2, it is 0, it is 1, it is 0. Which is most negative? This will enter. Which one is leave? This is 4 by 1, this is 6 by 2. So this will leave. In the first table itself, this is a pivot element. So what is the next table now? The next table will be, this is your S1 and this is your A2. In place of A2, you are having now H2. So you will make 1 here. This is minus 1 by 2, 1, 0, minus 1 by 2, 1 by 2, and this is 3, 1 by 2, and this is 3. This minus half of this is 3 by 2. This one is half of this 0, 1. Half of this is plus 1 by 2, 1 by 2, and this is 7, right? This plus the 0, 0, 0, 0, 1. So now artificial variable leave the basis. So now you can take S1 and S2 as our initial BFS to start the simplest iteration for our original problem. So the work of phase one is over now. Now we will go for phase 2. In phase 2, we will take this table as our initial table. Where constants are same, right? X1, X2, S1, S2. Now no need to take artificial because the role of artificial variable is over. So it is now 7, 3. It is 3 by 2. It is minus 1 by 2. It is 0, 1, 1, 0, 1 by 2, minus 1 by 2. And this is your S1, this is your X2. Now compute Zj minus Cj's of the original problem, taking the original objective function. So Cj's are what? Cj's are basically 3 and 4, right? So it is 3, 4, 0, 0, right? And cost of these are 0, cost of this is 4. So this will be minus 2, minus 5, this will be 0, this will be 0, this will be minus 2. So this will enter, and only this variable will leave. This is a pivot element. Now you can complete a table and you can find out the optimal solution. Right now, one can complete the table, complete the simplest iterations, and find out the optimal solution. Is it clear? Is it clear? Is it clear? Hello? Is it clear? Brinda? Okay. So I have given you a brief idea of simplest iterations and all. Now let us CJ is the first phase. The CJs in the first phase are from this objective function. So this is 0. X1 is coefficient of X1 is 0, 0, 0, 0, and this is only minus 1. Okay, Rupesh? Okay, Rupesh? Minus 1 is a coefficient of A1 here in the objective function. And why minus 1? Why minus A1? Because we want A1 to be 0. If A1 is non-negative, A1 will be 0, and we want to maximize the objective function, then A1 must be 0. That's why we are taking minus A1. If there are two artificial variables A1 and A2, we take minus A1 minus A2. Okay? Okay, okay, Rupesh. Now I go to integer linear programming problem. just give you an idea of what integer linear programming basically means. See, in many problems, we want to maximize or minimize C transpose X subject to AX less than equal to B, X greater than equal to 0, where all or some of the X bit are integers, right? Say X is integers and integers, we say. So means all X we want to be an integer value, right? So if you are taking all variables as an integer, so it is all integer linear programming problem. And if some of the variables are not integer, I mean non-integer, right? So basically, we are having either all integer LPP or mixed integer LPP. So if all the variables involved in the problem we need to be an integer, so we call it all integer. Otherwise, if some of the values are integer, some of the values are may or may not integer, we call it mixed integer linear programming problem, right? Now the question is that suppose you want to measure number of items in a manufacturing company. They manufacture, suppose, two products A and B, and they want number of items of A and B for which their profit is maximum, for example. So the number of items cannot be in fraction. So if to solve such problems, we need to have the concept of integer linear programming problems. So we have, now the question is, why not we can round it off, right? So we have examples where round off method will not work, or the nearest point method will not work. You might have, you see, you have this type of visible region, and suppose you are getting this point as an optimal point, which is not integer, right? So people think that why not we can find out a point which is closest to this point and which is all integer. No, this will not work. We have counter examples in the literature. We have counter examples, right? You might be thinking that why not we can make this as round off. Why can't we take? Because round off may also go outside this visible region. So this round off method will also not work. So we have to go for some specific techniques by specific methods by which we can solve integer linear programming problems. So the popular methods are basically branch and bound technique and Gomori's all integer method, right? And then Gomori's mixed integer technique. So I'm not going to much detail of it. If time permits, I will continue this maybe in the next lecture. So these techniques, those who are interested can also read, and these techniques are the popular techniques to solve any integer linear programming problems, right? There we introduce some cuts, right? Basically, what is the main fundamental thing of such problems, that we set some cuts or some additional constraints to the variable corresponding to the variable where we need to make an integer. and that constraint will reduce the feasible region, and will in that reduced feasible region we will try to see that whether there is some point which is all integer solution or not. If not, we again make a cut or additional constraint we put. We keep on moving, we keep on analyzing the feasible region till we get the all integer or mixed integer solution. If no, that means problem is infeasible. If you find such point, that means problem is feasible, and that is an optimal solution. So we stop here today for this session. Please discuss your doubts now. Please discuss your doubts. Hello, Rupesh, do you have some doubt? Okay. What about Brinda? Yeah, Brinda, for overdetermined system, we have different method, right? For overdetermined, we simply have least square technique, right? Normally, we have least square technique for solving overdetermined system. What about other Ankita? Any doubt? I don't know whether you are able to understand the things or not. Yes, Shanti Das. Okay. Any other doubt from any other person in this group? Others are not responding anything. Kirti, Neha, Priyanka, what about you? Okay, okay, Satinder, yeah. Yeah, that is also correct. So, okay, I will ask a few questions from you then. I have still have 2 3 minutes. Uh, so, uh, you just write through. You can write in your chat box, right? When we have a case of infeasible solution in simplex method. Yes. Okay, let us see. Rajesh Yadav, are you there, Rajesh? Rajesh, are you there? Rajesh. Yes. Shrikant. Shrikant, are you there? You can guess also. You can guess. Don't worry for the answer, but you can write something that this may be the case or may not be the case. The simple question is in simplex method, when you will be having a case of infeasible solution. So the answer is that this case will never be there, because what is happening in simplex method basically. In simplex method, the problem is applicable if you have this type of problem, right? You we already see. For this type of problem, simplex is applicable, right? And you can always see that x equal to 0 is always a solution. Is always feasible. No, no, Satinder, you see here. You see here. See, this is the problem. This is the problem. Yeah, yeah. Yeah, Brinda is right. Trivial solution is always there. Right. So this is a trivial solution x equal to 0, which is always there. Hence, the problem will never be infeasible. So we never have a case of infeasible in simplex situations. However, if we perform, if the problem is not following simplex criteria, then we have to go for two-phase method or Brigham method. And in those method, if artificial variable does not leave the basis, it means that the problem is infeasible. Right? So we'll stop here, and next we will meet at 4 p.m. And in that, we will first discuss some non-linear programming concepts, and then we will go for some decent algorithms, gradient algorithms, right? So thank you very much. Rahul ji?
Yeah, thank you, Professor Gupta. It was indeed a wonderful talk, very informative, full of knowledge. And the way you were delivering your talk, you were trying to explain